How's it going, AP Stats? Last couple pages here of our notes for Chapter 12, Part 2. So we should be on the page where we have matched pair design. So we've dealt with two different types of experiments already. We should have dealt with just the, the simple random, completely randomized design. And then we should have talked about block design in class. And then this matched pair design. This is kind of the last one, and this is really a special case. We don't see these too often, but it can come up. And what a matched pair design is, kind of, you can see it in the name, matched pair. It's a special case of randomized block design where each block will have two members or two participants or two subjects. And ideally, these two subjects are somehow related or somehow affect one another. And this can only be used when there are two treatments. We would say within each pair, treatments are randomly assigned. Okay, I don't want to go too much into detail with matched pair. The only thing really that you guys should kind of know from this is that this is the case. There are only two treatments in this type of experiment, and we block subjects in pairs. So if I had like 40 subjects, I would make 20 pairs. And in each of those pairs, I would give one subject treatment A, and I would give the second subject treatment B. And that would just go on following that same pattern with the remaining pairs. Okay, and depending on obviously the experiment and what it is that we're looking at, what are the variables, it may be more beneficial to create a matched pair design. But for now, we'll leave matched pair design at that. Okay, so we pretty much covered most of the experimental stuff. Just kind of a little quick review on what we've done. Subjects. Subjects and experimental units. Remember, these are the things that we're studying or the things that are receiving treatments. Treatments are the things that we are giving them. So remember, in some experiments, there should be more than one treatment, right? There should be at least two. Maybe a control group, treatment A, treatment B. And what those treatments are is we're changing the factor. So I kind of go back to that sleep study one, or maybe, let's see, if I wanted to see if sleeping with the TV on is worse for your sleep or if it's better for your sleep. So I set up an experiment and I take 20 people, I make them sleep with the TV on, and I take other 20 people, make them sleep with the TV off. There's two treatments there, right? One group is sleeping with the TV on, the other group is sleeping with the TV off. The factor, or the explanatory variable, is whether or not the TV is on. So this would be like TV. So these two are related. The factor is the TV. The treatments, we have two different types of treatments in that case. Levels, you can change the treatments. So like as of right now, we have two treatments I mentioned. Like one can have the TV on, one can have the TV off. But maybe I decide to add a third level, and maybe the group that has the TV on, maybe I split that up even further. So now instead of just having 2 treatments, maybe now I have 3. I have a group that has the TV off, I have the group that has the TV on, and maybe the third group, I'll say, the third group, you guys have the TV on for the first 30 minutes as you're trying to fall asleep, and then after 30 minutes, the TV shuts off. So levels are kind of just another way that we can split up treatments. Maybe that way we can see if there is some sort of relationship. So levels just goes kind of more into detail. Response variable is what it is that we're studying after the experiment. So in our little sleep study here, the response variables is we want to see the quality sleep that they got. Maybe we're studying how many hours of REM sleep they got or something like that. This is at the end, what are we looking at? What are we comparing between the subjects? Okay. What else did we talk about? We talked about the kind of 4 main things with experimental design, 4 big components. All right, the first thing that we talked about was control, right? We want to control as much things as possible, make sure that there aren't any lurking variables or other things that could affect our experiment. Like in this case, what if one of our subjects is like, I don't know, they're weird or something, and they drink like 5 Monsters at 9 p.m. every night. That could affect their results, which would affect our experimental results. So maybe we tell all of our subjects, like, guys, just try to keep your caffeine levels at a regular amount throughout this experiment. So we want to control as many variables as possible here. Randomization, right? We want to make sure that we can put these subjects into random groups where we don't pick what person goes to what group. We want to do that randomly. Replication, right? We want ideally more than 2 people in an experiment, right? We want more than 2 experimental units. We should probably have at least 10 for each treatment. And then the last one, let's see if I can remember. We had block, right? Block, I said, sometimes not necessary. Another way we can think about this is we should have at least 2 treatment groups. All right, so we want at least 2 different treatments, so like a control group and then another group. And obviously, depending on the levels, maybe we have 3 treatments, maybe we have 4 treatments. It really depends on the experiment itself, but for sure we want at least 2 treatment groups, a control group, and then treatment. Control versus treatment. All right, so we have that stuff. Just a couple other terms we talked about. We mentioned placebo. Placebo is when you kind of give a false treatment, like nothing really happens with the placebo. It'd be like me giving you this magic pill that, hey, this pill's going to make you do much better on your math exams. And all I gave you was like a plain sugar pill that does nothing. But maybe mentally that kind of tricked you and it helped you. But a placebo is kind of a fake treatment. We talked about blinding, so like a single blind and a double blind. So a single blind is where the subjects, they don't know which treatment they're getting. Or it might be that the research team doesn't know what treatment they're getting. In a double blind, it'd be that both the research team and subjects have no idea which treatment they received. Now, this makes sense with some experiments. In the experiment right now where we talked about sleep, it wouldn't make sense to blind the participants. Like, the participants are going to know if they're either seeing TV or if they're not seeing TV. Like, you can't fall asleep with the TV on and not know that the TV's on. Like, it's going to be there. But maybe we could have done a single blind with that experiment where the research team, maybe like the following day after sleep, and then they're looking at the participants. Maybe the research team has no idea whether this participant slept with the TV on or slept with the TV off. And when they're evaluating that person's sleep, there's some sort of blind right there because they don't know if that person slept with the TV on or off. And what that helps us do, what blinding does, is it helps minimize bias. All right. Let's see what else we have, guys. This last page, I actually want you to cross that out. A couple of things, and this is probably one of the key things with the experimental design. If you guys remember, I talked about observational studies more so last week versus experiments. And in experiments, we control things. Observational studies is more like surveys. We just observe things. And what can happen is, in these, we can make generalizations, where over here we can establish causal relationships or cause and effect relationships. Right? But now we can actually take this further. And depending on a couple of things, we can make better conclusions. So what I'm going to show you here is a pretty important table with experiments where we talk about randomization. So yes, we know that experiments can determine cause and effect relationship, but it's more specific than that. And it's more specific based on how we do randomization. So I'm going to show you this table, and the first part of the table comes to sampling. How did we gather our sample for our experiment? Did we do random sampling? Or did we do non-random? Okay, we talked about sampling and methods of random sampling, right? We can do simple random sampling, we can do systematic, we can do cluster, we can do stratified. Those are all methods of random sampling, right? And ideally, we want random sampling. So that's the first piece here, right? We want, ideally, random sampling. Okay, but now let's say we have our sample. Let's say I grabbed 40 people somehow. And now those 40 people in my experiments, I have to put those 40 people to 2 different treatment groups. So I have to put 20 in one group and 20 in the other. Now, it is very important that assignment, so assigning those people to the groups, is also done random. So I would have to randomly assign those 20 participants to one group and the 20 other participants to the other group. So within your experiment, we need to make sure that our sample is random and we're randomly assigning them. Okay, and here's how this affects what conclusions we can make. If we gathered a random sample and we made a random assignments, this is the best case scenario. We have a causal, let me change the font here, or the size. We can establish a causal relationship in population, which is good, right? We can say that TV causes people to lose sleep for all U.S. adults, or whatever population we're studying. Like, we can literally say that because we took a random sample and we randomly assigned. Okay, now let's say we did not take a random sample. Maybe we asked volunteers. Maybe we had to conduct our experiment with volunteers. So maybe we had 40 volunteers, but we still assigned those 40 volunteers randomly, right? So what we can do with this is we can establish still a causal relationship, but not to the entire population because we didn't take a random sample. We can establish a causal relationship in the sample only. And honestly, most experiments, this is where they are. It's not really realistic to always get a random sample, a truly random sample, when picking your participants. Okay, kind of moving on here. This bottom left box, this would be that we did gather a random sample from our population. Somehow, maybe I did a simple random sample, but I didn't randomly assign them. Now, this would be a very bad experiment because you should always have the ability to randomly assign them, so why wouldn't you? But in the event that you did gather a random sample but didn't randomly assign them, you can detect relationships but not causality. So this would be pretty similar to observational studies. You can put that in there, kind of like observational studies. And the last one, this is kind of really bad. We conducted some experiments. We didn't grab a random group, and we didn't randomly assign them. This is, again, we can detect relationships in sample only. So we can't do causality. Over here, the relationships, we can make general statements to the population. Over here, we can't make general statements to the population. It's kind of stuck to our sample only because we didn't gather a random sample.